Hi, this is Seth again, and this is part two of our lesson on change of variables. And we just did a problem where you could use both the CDF and the change of variables formula, and we verified that we got the same results. But that's not always going to be the case. Sometimes you're going to be able to use the change of variables formula and not be able to use the CDF method. And sometimes you're going to only be able to use the CDF method and not be able to use change of variables. And it's important to kind of know and be able to distinguish between the two types of problems, which is where problems 2 and 3 are going to come in. So problem 2, say that x is normally distributed 0, 1. Then what we want is the PDF of y equals x squared. So, back from problem 1, I can kind of copy this strategy down to see if it applies, right? But the first thing that I notice is when I write down y equals g of x equals x squared is not strictly increasing. It's not even injective, right? It's not strictly increasing. It's not strictly decreasing, which is bad. And since our change of variables formula, requires g to be this differentiable, strictly increasing function, we can't actually apply this formula. So, all the nice stuff that we did in the last problem with change of variables kind of goes out the window. So if you were to apply change of variables here, you would be very sad, and things would end in disaster and disappointment. So, I think that actually the best way to solve this problem is just from first principles using the CDFs. And I'll do that real quick. It doesn't really have much to do with the change of variables formula, but I think it's kind of nice, and it'll teach you about the chi-square distribution. So, Fy of y is equal to the CDF. And right away, we can just replace this with x squared, which is less than or equal to y. And then I can take the square root of both sides, but, if I do this, because I'm taking the square root, I must consider both the case where y is, the square root of y, like a negative side and a positive side, basically. So I'm going to write this down, and maybe we can think about why it's true after the fact. Right? So, when I take the square root of this, I would like to take the square root of y, but x could also be negative, right? And that would give me, some, value of y as well. So I really have to consider like negative square root of y and positive square root of y. Okay? But I know what the CDF of x is, right? It's just phi, the CDF of the standard normal. So if phi is the CDF of the standard normal, then I know that this is just phi evaluated at square root of y minus phi evaluated at minus square root of y. And then just a little trick, remember that phi, of something negative is equal to 1 minus phi of that positive thing. So this actually evaluates to 2 phi square root y minus 1. Because if I just, if I do this minus this quantity, then I get 2 phi at square root of y minus 1. Okay. Then what I want to do is I want to directly take the derivative of Fy y to get the PDF, right? I don't exactly, know how to do this in closed. I don't really know I don't really want to write down the PDF of the normal. So what I'm just going to do is use phi to be the PDF of the standard normal, which, is just this guy here. I just don't want to write it all out. You could, but I'm not going to. So 2 phi evaluated at square root y, times by the chain rule 1/2 square root of y, 1 over the square root of y. Or you could also write this as I think this is probably a little cleaner, y to the minus 1/2. Okay. And the nice thing about this is the 2's cancel. So you end up getting the PDF of the standard normal times y to the minus 1/2. One last thing, what's the support? So x is standard normal, so x is in minus infinity to infinity. If I square anything in minus infinity to infinity, then I get y in 0, to infinity, which is exactly the support that I'm going to write down. Perfect. Okay. So this is an example where the change of variables formula doesn't actually apply, and you actually do need to work directly with the CDFs. This is actually like a well-known distribution that a lot of, there's been a lot of papers written about, and it is very famous. It's called the chi-square distribution. So I'm just going to kind of run through that really quick. You may have exposure to it, or you may not, but this is the chi-square distribution. If you have zi's that are IID standard normal, then if y is equal to the sum from I equals 1 to n of the zi squared, then we say that y is chi-squared distributed with n degrees of freedom, or equivalently, it's gamma distributed n over 2 1/2, where n is the degrees of freedom, and it's also the number of squared standard normals that you're adding up. So that was kind of an example where you can't use change of variables. You have to work with the CDFs directly, and a fun problem that I think introduces the chi-squared, which is kind of nice. So yeah, I hope to see you in the third part.